Hello everyone, my name is Jiacheng Tu from the University of Connecticut, Department of Electrical and Computer Engineering. Today I would like to introduce my research paper titled as Estimation of Machine Parameters in Exponential Serial Lines using Feedforward Neural Networks. Here is the outline. First, I will give the background and motivation. Second, I will introduce the system model used and the problem in the paper. Next, I will show how to choose the input data. Then, numerical experiments are presented. Finally, it is conclusion and future work. With the movements of Industry 4.0 and the advancements in Internet of Things technologies, such as flexible sensing, communication, and data computing, traditional manufacturing enterprises are transforming toward smart factories. New technologies, especially information-based ones, are rapidly implemented in modern manufacturing, which are aimed at finding new ways of production, decision-making, and better service responses in industrial manufacturing systems. In this situation, data analysis plays an important role. Moreover, a rigorous model-based approach would be desirable in handling such data, but construct such a model is not an easy work. First, it doesn't have a set of standard first principles, which can be used, leading to a unique solution in traditional electrical and mechanical systems. Second, another step for modeling is to identify the parameters of the machines and buffers in the model using factory floor production data. While in this step, it requires solid training, extensive experience, and a significant amount of time for different practical situations. So, in this paper, we will focus on parameter identification and find a new way to solve the problem mentioned above. This figure shows the system model we used in this paper. The circle represents the machine, and the rectangle represents the buffer. It has m machines and m-1 buffers. Each machine obeys the exponential reliability model and is defined by its breakdown and repair rates, lambda I and mu I. In addition, each machine is characterized by its cycle time, tau I, and machine capacity, Ci. This paper focuses on synchronous case, so it assumes Ci equals 1. The buffer capacity is Ni. According to these definitions, the average up and down time of an exponential machine is given by these equations. These three parameters are needed to be estimated in our problem. Since average uptime is related to downtime and machine efficiency, we only need to estimate average downtime T time and machine efficiency E. The goal of this paper is to identify the parameters of exponential machine. The traditional way to identify machine parameters is to estimate machine parameters directly from machine status data. However, it may require more complicated data collection infrastructure and data aggregation techniques. For Bernoulli serial line models, this can be accomplished by taking advantage of the analytical expressions of throughput and working process as functions of machine parameters. But this method becomes impractical for the exponential serial line model considered in this paper, since the analytical expressions for performance evaluation in exponential lines are much more complicated than the Bernoulli case, so it is essential to turn to a new method. In this paper, we construct a black box model that characterizes the relationship between system performance metrics and the machine parameters. As machine learning is gaining success in an ever-growing range of applications, this paper studies the feasibility of applying fundamental machine learning methods in solving the parameter estimation problem. Especially, we use one of the most widely used feed-forward neural network models, backpropagation neural network. Then, to estimate the machine parameters by neural network, we should choose the input data firstly. The data should be easy to measure in practical applications and have low data ambiguity. So throughput and working process are considered. Throughput is average number of jobs produced by the last machine of a production line per unit of time in steady state. And working process is average number of jobs contained in the ith buffer of a production line in steady state. But we don't know if knowing only the throughput and working process can uniquely determine all machine parameters. So consider an exponential line with two identical machines and with n equal to 10. We fix throughput and search for the combinations of machine parameters that lead to the same throughput. Since two machines are identical, it guarantees the same working process. From this figure, we can see different curves represent the different throughput, and in the same curve, we have different combinations of T down and E that can lead to the same throughput. So we should find other input data. While machine parameters can be readily calculated if machine status data are available, the definitions of machine status can be subjective, and the collection of such data may not be convenient for many small and medium-sized manufacturers. Therefore, we again turn to the job floor data. When monitoring job floor in practice, it is possible to obtain the fraction of time when a buffer has a certain number of jobs. In the framework of the exponential production line model, this amounts to the stationary probability distribution of the buffer occupancy. To add the buffer occupancy distribution data into the input variable set, we choose two boundary probabilities, P0 and Pn, and the probabilities of H in the following k intervals. Since the input data has been selected, numerical experiments are carried out. We started from two machine lines. The input data is throughput, working process, buffer capacity, P0, Pn, and three probabilities of H. The neural network has one hidden layer, and it has 20 neurons. The performance goal is 10⁻⁻⁵, and the learning rate is 0.001. 50,000 two machine lines are generated with the system parameters randomly and uniformly selected from this range. 40,000 lines are labeled as training data, and 10,000 lines are labeled as testing data. The experiments are based on MATLAB Neural Network Toolbox. Here is the two machine lines result. It shows that neural network models can estimate the parameters of an exponential serial line with good accuracy. The estimation error for machine efficiency is only about 0.3%, while the relative estimation error of T down are less than 2%, and the T up into machine lines are less than 2.5%. The table 2 shows the performance metrics computed by estimated parameters. The first row is mean relative error, and the third row is mean absolute error. The error between true lines and the estimated lines are rather small. Then we will give an example. Consider a two machine line with these parameters, and the estimated line is calculated by neural network. We compute two lines' performance metric. The result shows that two lines have almost the same throughput and working process. The figure is buffer occupancy PDF for two lines. We can see two curves are nearly the same. To explore the properties of two lines, the variation tendency of performance metrics with the parameters are given. The figure shows the trend of performance metrics with the variance of first machine's efficiency from decreasing 90% to increasing 60%. X-axis represents the proportion between new parameters and the parameters before variance. Similarly, this figure shows the trend of performance metrics with the variance of the first machine's downtime from decreasing 90% to increasing 100%. Both of two figures represent that the estimated line and the true line have the similar properties. Then we extend to 5 machine lines. The parameters of neural network are almost the same as 2 machine lines. The only difference is the number of neurons in hidden layer is 30. The 50,000 lines data for 5 machine lines are based on simulation. Compared with 2 machine lines, the parameter estimation errors for 5 machine lines are elevated, but the results still remain at a decent accuracy. Moreover, as shown in Table 2 and Table 3, the system performance metrics under the estimated parameters are still very close to the one under the true parameters, less than 1% for throughput and working process, and under 0.01 for all probabilities considered. Here is the 5 machine lines example. Consider a line with such parameters, and the estimated lines are given by neural network. The comparison of the performance metrics is summarized in 2 tables. Apparently, they are very close. All errors are less than 0.5%. Figures show that the PDF for each buffer under the estimated and true machine parameters. As one can see, both probability distributions for the same buffer exhibit very similar trajectories. From the statistic results and illustrated by the examples, the estimated parameter, although not exactly the same as the true parameters, it can still approximate the dynamics and the stationary behavior of the system very well. To explore the property of performance matrix between estimated and true parameters, another 5 machine line case is given. The figure shows the trend of performance matrix for the first buffer. The first machine's efficiency varies from decreasing 90% to increasing 30%, and downtime varies from decreasing 90% to increasing 100%. The results are based on the simulation. 2 figures represent that the estimated line and the true line have the similar properties. The improvement for estimated line can present the behavior of the true lines for 5 machines. In this paper, we apply the feedforward neural network as the learning model and use the production line's throughput, working process, and buffer occupancy probabilities as the input variables. Numerical experiments are carried out for 2 and 5 machine lines, and the results show that estimation accuracy is quite promising. The properties of lines with high estimated errors are analyzed, and the approach to evaluate the estimated results are given. According to the experimental results, machine learning-based approach can estimate parameters with high accuracy. Here is the future work. In the future, we will extend the study to more sophisticated mathematical models, explore alternative machine learning methods to improve estimation performance and computational efficiency. And finally, we will apply the results to manufacturing practice. Thank you.